Hello everyone, today we'll talk about the problem distribute coins in binary tree. We're given a binary tree that has the same number of coins as there are vertices, distributed in an arbitrary way among those vertices. So maybe all the coins are in a single vertex, maybe in two different vertices, maybe they have one coin per vertex, and that last situation is what we want. We want every vertex to have exactly one coin. And one move is to move a single coin between two adjacent vertices. So essentially one guy gives a coin to their neighbor. And you want to now make the tree have exactly one coin per vertex in as few moves as possible. Now this is a medium problem, that's how it's classified. I'm not sure if I would call it a medium, it's definitely not easy. And it could maybe be a hard. I think it's a medium because after you get the idea, then the code is very short and not complicated, right? This is the whole code. Also, it's not something that requires any special observations because it utilizes a standard technique, and I just think that this technique is maybe not something trivial to many people. So it's typically called tree dynamic programming, right? 3DP. But for many people and in many implementations, this is simply just DFS on tree, right? And you can see that DFS-like situation going on here in our code because we have a function and that function recurses to the left, to the right, and returns some result. We just run that function and it gives us the result for the whole problem. Anyways, if you're familiar with that idea, then of course after making just the basic observations you'll be able to solve this problem. And maybe if you're unfamiliar with it, you might also be able to just stumble upon this schema that solves problems like this. Okay, so how can we come up with a solution to this problem? Well, since we have a tree, let's say that we have something above us, we have a vertex, and that vertex has some two subtrees. And this is just part of the tree, maybe in the middle of running the algorithm. So what are some things that we can notice? Well, one thing that is pretty simple to notice is that when it comes to coins moving from node to another node, so moving along edges, then we can easily assume that through a given edge either no coins will flow, or coins will flow in one direction, or coins will flow in another direction. Are you able to prove the fact that it will never be that in the optimal solution some coins will, for example, flow here upwards and also downwards? That proof is very simple, because if some coins flow up and some coins flow down, then we could instead just not make the coins that flow up. The same number of coins flowing down we could also stop from going down. And now we would have fewer number of moves, and those coins would be exactly where they should be, right? Because in this case we're essentially exchanging identical coins between those two neighboring vertices. So essentially for every edge, we know that at the end we'll be able to either tell that it'll always transfer coins upwards or downwards, or maybe it won't be used. However, our situation is even simpler than that, because we can easily decide which of those situations it will be. Now, of course, as we know that we have a tree, and one of the most important properties of a tree is that every edge is the only thing connecting the tree to the subtree below it. Right? So this is the only way to transfer coins from this region to the rest of the tree is exactly through this edge. That's a property of the tree that is often used when it comes to solving problems, especially like this. And how do we know in what directions coins have to flow through this edge? Well, we have to count how many coins we have in this subtree. Because if in this subtree we have exactly the right number of coins, so exactly the number of coins equal to the number of nodes in this subtree, then we, in principle, don't need any more coins or any less coins. One way to see that we should use only the coins here is that, of course, if we take some coins from outside, then we have to, at the end or before, give some coins away. So this is the situation that we said was illegal. But it's also quite simple that, yeah, of course, we want to use coins here. We don't want to move them outside and then take some coins from the outside if we don't need to. So by looking at the number of nodes here and the number of coins on all the nodes here, we can say if they are equal, then we don't have to use this edge. If we have more coins than nodes, then we have to get rid of some of those coins, exactly of the surplus of coins. So the surplus will travel upwards. And the same thing if we have a deficit of coins. If we need more coins, so the number of nodes is greater than the number of coins here, then we have to just take them from outside. So for every edge, we can, assuming that we know the size of the subtree below it, answer in what direction coins will flow along that edge. And now calculating numbers like this, such as sizes of subtrees, or in this case the difference between the size of subtree and the total number of coins in that subtree, this is a very easy use case for 3DP or for DFS on tree, because for instance for size, we have this very easy thing that this is 1 plus size of this and also plus size of this. So this is, because in general we can think about it as DFS, because we just, when we look at this, it's essentially a post-order DFS. When we look at the node, we first go into all its children and then we calculate its result from the children, or by looking at it as a 3DP, we just go from leaves upwards, because the size of a leaf is 1 and the size of a node whose children's sizes are all known is also known. It's 1 plus the sum of those sizes, right? And this is the general way in which we calculate things when we use 3DP. This will also be the thing that we calculate in our solution. So we know now for every edge in which direction the coins have to flow, and how do we get to our final solution from that. And the idea is to assume, when we look at the current subtree, that even if the number of coins is not equal to the number of nodes, that we can either, if we have too few coins, then we know that we have to get them from our parents, so we can assume that we already have them and act like we already have them. If we have too many coins, then at the end we'll have to give them to our parent, so we might as well just keep them in the root node. And in that case, it's feasible to calculate how many steps are necessary, how many moves are necessary to fix this subtree and have, for instance, an imaginary negative value on the root, or perhaps a value on the root greater than 1. And that's easy because we have to fix the left and right subtree, and now we have to get some coins to flow into those subtrees that require more coins, or perhaps take the coins away from the root of the subtree that has too many coins. So for instance, if our left and right subtrees, this one has a deficit, this one has a surplus, then if it has a deficit, for instance, of 3, then we know that we have to pay 3 to give this subtree, the root of this subtree, those 3 coins. And then here we assumed that we had those 3 coins already, so we don't have to consider any more moves. Same thing here. If we have a surplus, let's say, of 5, then we know that this surplus ends at the root of this subtree, and it has to travel to ourselves. And since at the end we then have a surplus of 5, which is not correct, in fact we have a surplus of 4, because now we also have to leave 1 coin for ourselves. I did say 3, 5, I didn't mean that. That means, of course, because we give this one, so it's 5 minus 3, which is 2, minus 1, which is 1. So we have a surplus of 1 coin, 1 more coin than necessary. And that 1 coin will have to travel upwards, but we don't care about this right now. So we just leave that additional coin in our root. And after that, since the number of coins in the whole tree is exactly equal to n, if we do that and we end up at the original root of the tree, then it will have exactly 1 coin and we won't have anything else to fix. And this is exactly what we need to solve this problem. So we'll be calculating both how many coins are needed, so either the surplus or the deficit, which would just be the count. So this is the difference between the number of coins and the size of the subtree. And also the cost that we already incurred to make sure that every subtree is, so for every subtree we have that cost, so that the subtree is already in a nice state. So every node has 1 coin, and the surplus or the deficit is in the root. And so now, the total balance, the total count, is the same thing as the count to the left, count to the right, so the surplus or deficit to the left and right, plus the number of coins we have, minus 1 because one coin has to stay in the root. So that's simple. And how much do we have to pay? Well, we still have to pay all the moves for the left and right subtree. And also for the deficit or surplus in our subtrees, we know that for the deficit we have to push those coins downwards, for the surplus we have to push them up. But how much? Well, here we have a 3, here we have a 5, so those are exactly the absolute values. Because a deficit would be a negative value, so it would be a negative 3, and we want to just take the 3. So just the absolute value of the difference between the number of coins available and the number of nodes there. And we just return this pair. And after doing all that, starting at the root, we just have to say how much we had to pay in total. I think it's easier to calculate both the count or balance and how much we have to pay for every node, because those things are calculated in the same way, along the same DFS, along the same 3DP. But of course, since this pay is just the sum over all the nodes of what they contribute, it could also be just one value outside of the function which we just add to the global counter, and then we just have simply counting the counts. But I think this one is easier to see that this is indeed simply just a 3DP or a DFS on 3.